Um, okay, everyone, good morning. So I will be doing the introduction for parallel computing today. So we'll be looking at what we are looking at when we are talking about parallel computing. What is the definition, what sort of things, and what are the basics behind doing a parallel computing. Okay, so first of all, before we start in, we should know something about serial computing, right? We can't talk about parallel computing unless we talk about serial computing. So the way our computers, the current computers are architected is in a way where we have a problem. Okay, anything that you feed to your computer is going to be a problem. Okay, and this problem is chucked down or get into smaller pieces, and the problem is break down into smaller pieces, something what we call instruction. And these instructions are executed through a processor. Okay, so at a given time, these instruction will be feed into one of the processors, and the processors will execute this instruction. And after the problem, all the problems, after all the instructions are executed, we can consider the problem to be solved. Okay, so it does not matter what is the problem is. It might be a mathematical logical question, it might be an image manipulation, it can be playing a song, it can be doing a network request. Whatever the problem is, the problem will get drilled down to small instructions. Then this instruction will get executed through a processor. So most of the time, actually we can't say like now most, because it's slowly going away. So instructions, these instructions that we have with chunked down to the problem chunked down to instruction, and these instructions are fed into a processor for a single processor in a sequel manner. That means at a given time, let's say the time is t1, at a given time, one single instruction will be fed to the processor. At a given time t2, another instruction will be fed out. So list goes on. Like until the problem is solved, one by one, the instruction will be fed to a processor. So first thing that you guys need to remember, instructions, the problem get chunked down to instruction, and instruction will be executed at a given time. At a given moment, only one instruction will be executed. Okay, that is the definition of a serial computer. Okay, so you can't expect at T1 there will be two instructions executing at the same time. No, that is not how a serial computer works. You have a processor, and this processor will execute and only accept one single instruction at a given time. Okay. In construct, this is okay for most of the instructions that we do. Most of the instructions that we execute these days, and you might find this this one is not that efficient, but believe me, the speed that this instruction get executed is what matters. Okay, even though this is a single problem break down into small instructions, if the frequency of executing this instruction is very high, you can get the problem solved very quickly. Okay, so that is the theory behind what we are going in a serial computer. Most of the time, the execution that we do in our day-to-day activities are serial computing. Okay, we are not doing parallel computing even for most of the 90% of our daily work. Okay, most of the time, the instructions that we execute using our CPU is going to be in something like a serial computing or serial manner. So instruction will get executed in a processor using one single processor, and these instructions are executed very frequently. So the problem get executed very fast. So if you guys might have seen applications like your computer is using the same instruction set, or if you guys have seen something like I'm not sure, single board computers you guys might have seen, where you have like IoT devices. Okay, so IoT devices tend to have this serial execution. That's because of the limitations of the processor that they have. So I have to happen one single IoT device, IoT chip that I think you guys can see. So this is one of those processes. I'm not sure whether you clearly see in the application in your camera. So this is one of the boards, one of the processors. It can execute instruction in a serial manner. So these chips are designed to execute instruction in serial manner. So they will have instruction going on. The instruction will be fed to these processors, and they will be executed in serial manner. They do not have parallelization at all. They will be doing the instruction in a serial manner. Okay, so basic things. Serial computing, we have a processor. Processor will be only executing one instruction at a given time. Okay, that's the bottom down explanation. So we go to parallel computing. Obviously, you guys can see how parallel computing works in this sense. So it's gonna simulate multiple computing resources to resolve computational problems. So the problem is there. The instructions are chunked down, or instructions break down. The problem is break down to small instructions. Okay, and the processor is capable of handling multiple. There can be multiple processes, and these multiple processes will be executing several instructions at a given time. Okay, so if you guys can see the given time t1, at t1 the problem will be executed. Actually, the instruction will be executed. 4 instructions will be executed at t1 at this given architecture. Okay, so problem need to be breakdown. Okay, so this problem can be break down into 4 different sections. Okay, the whole thing is representing our problem. Like in here, this whole block represent the problem, but in here the problem is whole 4 of these block. And first thing that we need to make sure in parallel computing, whether we can do the problem can be break down into different sections. Okay, if the problem is not able to break down into several small problems, then what we can't do is parallelization. Only if the problem can be chunked down to these 4 different sections, and one chunk of that problem can be break down to instruction, and we can feed it to processor. Okay, so so you guys can see when we are looking at parallel computing, it is not going to be easy as it seems in serial computing. Okay, the problem needs to break down into discrete parts. Problem should be able to have discrete parts. Okay, that is one of the requirement of parallel computing. The problem should be able to break down into discrete part. Okay, that is the requirement one. If you are not able to if you're not able to break down the problem as a whole, then it is not able to be parallelized. Okay, so in this scenario, the problem can be breakdown, then it can be parallelized. Okay, series instruction from each executed simultaneously on different processor. Their overall condition happened between each part were executed. So you guys can see the problem got breakdown, and there are instructions, and the instruction at a given time is fed into the processor. So the processors can be executing the same instructions. Most of the time, the instruction is going to be same, or at least at a given time, the instructions are ready for processor to execute. Okay, so you guys can see this is the serial computing architecture or structure and the parallel architecture. Okay, so the problem, what we're calling in parallel computing, the thing that we are trying to solve, should be able to broken into discrete part. Piece of work can be solved simultaneously. So these are the requirements for these things. Unless we are meeting this requirement, we can't parallelly execute a problem. So these three points are really really necessary. So we have to have the problem in discrete part, execute multiple program instruction at a given moment time. You can see that it should be able to execute one or more instruction, multiple instruction at a given time. Okay, this should be met. Okay, be solved in less time with multiple compute resources rather than a single computer resource. So the next thing that most of us does not get is in parallel computing is the execution time for this. Okay, so for instance, we have a problem. Okay, we have this problem, and the problem can be can be um, break down into discrete parts. Okay, the first check is done, and the second check is this instruction should be able to execute simultaneously for the given processes or given resources. Okay, that is also checked. But the most of the time, what we do not get is the execution time. Okay, so these instruction were breakdown executed, and we got the result. But if we can get a problem, okay, without breaking down to discrete part and getting the instructions, we just execute this one serial. If we can get this executed serially, and if we can get the result, okay, any that we can get a problem executed in serial as well as in parallel. But the time it takes a parallel computing algorithm or parallel architecture, the time it takes to execute this should be less than a serial computing doing the same thing. Okay, so you guys can see there is added complexity in parallel computing that is breaking down, executing instruction, and once the processes is executed, sorry, once the processes are executed, those should be the result should be collected all together, then it is shown. But in a serial program, you just have the problem, chunk it down, process it, and get the result. Okay, so we have this dilemma that's saying if we can get things executed parallelly, then it will be much faster than serial. No, that is not the case. That is not always the case. Sometimes the complexity handling with these things, the instruction to be breaking down and executing parallelly, and the process of doing this is taking a little bit of time. The process, the preparation, and the once these executed, getting all these result together and executing all these things most of the time the parallel computing happens in different device, the IO bus and everything. The complexity of parallel computing is high, and the time it takes to prepare these things and get the final results sometimes is overwhelming. Okay, so the same problem, if you feed it to single serial computing, it get resolved immediately. So the problem, let's take a hypothetical scenario. We have a single problem. If you use parallel computing to chunk down to get instruction executed and processed and go all together, it will, let's say, take 10 seconds. Okay, it's 10 seconds parallel computing to do this task. But at the same time, the same problem, same instruction set, get executed in a single processor. They don't have to go the hustle like parallel computing does. It can get these things done in 5 seconds. Okay, if it is getting down by 5 seconds, then we need to really think about the execution time. Okay, so the execution time for parallel is 10, for serial it is 5. Then you guys can see the efficiency of the serial computing, a serial algorithm in this case is more efficient. Okay, it's take 5, this one takes 10. So what we need to consider the timing perspective in here as well. If we can get the problem done in a serial computing architecture with less time, then we do not use parallel computing. That is waste of resources, waste of time. Okay, so that thing need to be remembered as well. So the time that takes to execute to get a problem resolved is matters. Okay, that is one of the concerns. Okay, we will get into more concerns like memory limitations, data limitations. There are a lot of things to be considered, but overall, remember the time it takes a problem to be solved in serial computing. If it is less than the same counterpart for the parallel computing, do not go to parallel computing. You just do it in a serial way. Remember, the serial execution model works even as today. Most of our machines, most of the CPU related things that we do is doing by serial computing. Okay, not parallel computing all the time. Okay, so what are parallel computers? So this is the computing architecture. So the computers, what are the parallel computers going to look like? So how do we achieve parallelism in our computers that we use today? Okay, so we have you guys, I think, followed the basic architectural pattern of modern day computers. So you guys should know about the terms that I'm talking about the cache, cores, and threads, those kind of things. But if you're new, we can go a little bit of introduction. So to achieve parallelism, the computers are designed in a way they have multiple functional units. Okay, we have caches, we have GPUs, and we have CPUs. If you guys know that, even the latest phone models like iPhones, they have a separate module or separate functional unit for GPU processing rather than the CPU. When you guys must have heard the term the bionic chip, the A1 chip. So those chips are designed in a way we have a CPU and we have a GPU for doing some parallel tasks. Okay, so most not computers, but also phones that we have are capable of having multiple functional units. So using those multiple functional units, we can achieve parallelism. Okay, we'll see how we use GPUs to achieve parallelism, but these are the enabling factors. These are the enabling factors that a computer gets a parallelism in the first place. So we have caches. Uh, we are talking about L1, L2 caches in the CPU, and we have um, multiple caching levels, and we have GPUs where we can offload our workload from CPU to GPU. So these kind of multifunctional units help us to build parallel computers. If we do not have these multifunctional unit, we might not get a parallel computer in the first place. Okay, so these are the enabling factors for a multiple parallel computers. The next thing is multiple execution units or cores. That means in most of our machines, in the day-to-day machines that we are using, you will get the notion of there are like 12 cores, there are 8 cores. That that basically means our computer is capable of executing multiple instructions or uh, multiple problems at a given time stamp or a given time moment. There will be multiple resources where we can execute our instruction. So by using multiple cores, okay, within a one single CPU or central processing unit, there will find multiple cores. That means 8 cores or single cores. Those are like separate logic execution units. And sometimes in supercomputers or even some high-end server computers, you will find multiple CPUs, multiple processing units, which has multiple cores. So if you have 2 separate CPUs, then you have multiple execution units. Okay, yeah, and if you have one single CPU and multiple cores, then it's also a multiple execution cores. So by providing multiple cores, by providing multiple processing units, you will achieve parallel computers. Okay, the parallelism comes from these kind of implementations. And there are like these multiple hardware threads. Okay, these like the Hyper-threads by Intel. Right now, as of today, these are not in use, but they were one of the enabling factors for parallel computers. But nowadays, you won't find this in computers. So yeah, to enable parallelism, we have multiple functional unit, we have multiple execution units. So these things are enabling us to get into parallel computers. So if for some reason we cannot achieve one single parallelism in one single computer, then we have what we call multiple computers. Okay, that is also one way of getting parallelism in modern days. Okay, if we can't achieve parallelism in one single computer, what we do is we take a network and we link several computers. We call these things as node. In this case, we will have several computers over a network, and we connect these computers over a network, and we can achieve the parallelism over here. Okay, so you guys can see that a single node is identical to each other almost every time. Sorry, the node that we create, one of the nodes that is executing. So each and every node can execute instructions or problem parallelly. Okay, this one is like really really huge problem that we are talking about, because you guys can see the instruction should be the problem should be break down into different discrete parts, and all those problems should be able to feed into different nodes within the network, and the nodes will execute the instruction separately. And once those problems, discrete problems, are done, we have to send the result by network and get these things all together. Okay, so this is very high-end computing that we are talking about. We are not talking about counting from 1 to 100 or 1 to 1,000. We are talking about simulation of simulations of high-end physics model, maybe a cure for corona, that kind of computing power, a virus mod thing that requires a lot of computing power. We are talking about supercomputer level or supercomputer level in this architecture. Okay, so day-to-day activities, we will find less use cases, but if you are in a supercomputer or a highly parallel task which takes years to complete in a serial computer, we are talking in a network related parallel computing. Okay, so you have several ways that you can achieve parallelism. If you are in a single machine, you have multiple functional units, you have multiple execution unit. So by using these technologies, we can create a parallel computer. Or if you have more sophisticated need, you can have multiple nodes. These nodes are representing a single computer. These nodes to be interconnected using a network, and the problem is shared among these nodes and executed and get the final results back. Okay, so these are like extreme cases, very high-end cases. These things are like normally what you will see in day-to-day activities. But either way, you get the parallelism done one of these ways. Okay. So any questions up until this case? If you have anything, just interrupt me anytime. You have the chat, or you guys can have the raise your hand option, and I can answer any question if you guys have. Okay. Any questions so far? I think these are like plain old theories. Okay, so far so good. So we would ask the question, why parallel computing? If it is not always the use case, sometimes it is not helping. If it is not the best, always the use case, why we use parallel computing? Okay, the simplest answer is the complexity. The complexity of the things that we handle with, the complexity of our data, complexity of what we are trying to achieve, what we're trying to resolve. So in a problem, okay, what we are trying to solve can be complex. Okay, we have small problems like doing a small mathematical mathematical calculation. For example, we are taking 100 plus 200. Okay, the obviously answer is 300, that we can do in our brain even. Okay, even a small calculator out there can do that. Okay, but it is not always the case. There are, in our example, we use only two inputs, 100 and 200, and one operation, summation, and we get the result. But in real world, this is not the problem. This is not how the real world works. The real world is very complex. It contains lot of inputs. Okay, it contains a lot of operations that we need to do. So in a scenario uh, where the inputs are complex, where the outputs are complex, the operations are complex, then what will happen to the jobs that we get that we need to execute? Okay, to how to solve the problem. If the problem has thousands of inputs, if the problem has a lot of variables going on, okay, so that kind of problems is not something serial computer can achieve. Okay, we will see what sort of problems out there that requires this kind of parallelism, this kind of things. So interrelated. So we'll go through the paragraph in here. The real world is complex. That is true. That's what I told you. Events are happening everywhere. So many inputs, so many outputs. In real world, it is not like calculating 100 plus 200. Okay. Interrelated events are happening at the same time, each of these happening at the given temporal sequence. Okay, so the other thing is like 100 plus 100, the two instruction set happen separately. But in a real world, we can have multiple things happening at the same time. Okay, multiple things happen at the same time. So in a scenario where we have multiple inputs happening at the same time, the serial computer fails. Why? The serial computer can only comprehend one instruction at a given time. Okay, but in real world, with a given single time, it can happen multiple events. Multiple instructions can be happen. Okay, so in a scenario where we have multiple things happening at a given time, the serial computer fails. That's why that's the reason is serial computer is designed in a way it can only execute one instruction at a given time. But in real world, so many inputs have changing, so many events are happening at a given single time. So you guys can see that parallel computers can handle that kind of situation. Okay, so the second reason is that the first one is complexity. The third one is in real world what we are trying to solve. In real world, there are so many inputs at a given time. So to calculate such needs, relations were processed to parallel computing, the way make some sense of the data to modeling and prediction. Okay, so in a serial computer, you can't model these inputs because in serial computer you do not have multiple instruction execution. Okay, so you can't model these kind of real problems in a serial computer. So what we need to do is to match the reality, to match the complexity of these events and those events happening at a given single instance, we will need multiple instruction happening at the same time. So for better understanding of the problem, so better modeling, simulation, and understanding the complexity, the parallel computer is the only way that we can resolve these things. Okay, so this has to do with the real world phenomenon that is happening. The world is not serial at all. The world, the rate that things happen is complex. Everything happens in parallel. So real world phenomena, real world situations cannot be mapped into serial computing. Uh, so we need to use parallel computing to mesh the real world. Okay, so the real world problem can be executed, can be mapped only in the parallel computing. Okay. So remember, when we are talking about parallel computing, it is trying to resolve something complex, that is something in the real world. Okay, that's how the parallel computing is coming to play. It is not trying to resolve like small instruction execution, but a real world execution at a given time. Okay, and let's see what are the advantages of using. Uh, so advantages of using a parallel computing is obviously it save time and money. Okay, so this is like a generic advantage, if you like to say. In theory, throwing more resources at a task will shorten the time of completion with potential cost saving. Parallel computers can be built from cheap commodity components. Okay, so how we gonna achieve that? So if we have multiple resources to be work, okay, we have multiple resources where we can utilize, and we can get the work done by using those multiple resources. Wouldn't it be saving our time? Yes, time. And when we are saving our time, uh, we will get more and more potential saving when we are saving time. For example, let's take a real world example. Okay, so we have a land to cultivate. Okay, so we have land to cultivate. So if one single person is used to cultivate this, I mean the preparation of the land, if one single person is used, it will take 100 days. Okay, so it will take 100 days to one single person to get this done. But uh, the average cost for a labor, let's say 100 rupees. Okay, a person had to work 100, will work for a day for 100 rupees, and he will work 100 days. So the cost is 100 by 100. Okay, that is the cost, and it will take 100 days to complete. But in the same manner, let's say we take 10 workers. Okay, we have 10 workers, and we assume that all of these workers are working at the same pace. Okay, they are not, they are identical in their working speed and everything. So a person would take 100 days, but if 10 resources were used, we can get it done by 10 days. But the cost is the same. Okay, since they are identical, we assume that we can pay them the exact amount. So the cost will be the same, but the time that we have reduced is like we can reduce 90 days from that. Okay, and you guys can see if we use 100 workers for that, if you use 100 workers for that, you can get this land preparation in one single day. Okay, so you have 99 days saved for you. And same goes if you have if you can get um, if you can get not 100 people but 200 people, then you can get it down by even furthermore. Okay, but remember, the land should be, the people should be able to cultivate or work in isolation. Otherwise, it won't work. Like, let's say, okay, then we will have 10,000 people. So it will be like within a few hours. So we have to gain the practicality. Can 10,000 people work on a single field? Okay, land preparation. Can everyone be put into that land? They can move around. Do they get do they have enough work to be done? So we have to make sure we balance this out. Okay, even though we have resources that we can utilize, we need to make sure the resources are incapable of handling these things, and those cost savings are in a manner that we are not overdoing that. Okay, so we need to balance always with our resources, because we can't use more resources and waste that thing. We have to be sure in a position where, okay, if we use serialization, it will this amount of depth. If we use parallelization, it will take this amount of depth. But we can't overthink of resource utilization. That might not be efficient as it seems. Okay, so we need to make sure that we are utilizing these things in a way we do not take into consideration uh, where we have a lot of things going on, but in a way we don't overutilize these things. Okay, so that is something to remember when we are talking when we are thinking about resource utilization. Okay, and of course we can save time by using several resources or multiple resources, but make sure you are not underutilizing or overutilizing. Okay. All right. Next thing that you guys get the picture where how we can save the money, but uh, in a cost saving way, we have to draw the line where we are using the resource. Okay, so we can have potential savings. So in real time, in the real world example that I use, if something can get something that was supposed to get in 100 days, if we can get done in, let's say, 1 day, what will happen is we have 99 days left. Okay, that might be that time can be used for something else. Something useful, something like harvesting more land area, or maybe get the crops earlier on. That kind of things we can use. So we have to make sure that we are using these kind of things in a potential cost saving way. Okay. All right. Next thing is parallel computers built from cheap commodities and components. Yes. So in terms of computing world, now the cost of getting commodities is cheaper. Okay, it's varies sometimes, but think in a world where we have multiple computers, and we can paralyze something. So we have the option of getting these commodities for cheap. For example, nowadays uh, with the latest GPU innovations and all, the GPU prices are very low. Okay, so you can utilize GPUs for taking into actions in your parallel computing. So we need to have we have the capacity of buying parallel computer components for cheaper price. The hardware is cheap, the hard disk and all those kind of things are getting cheaper and cheaper. Community wise, we are seeing a lot of things going in a direction where things are very cheap to get, and we can use these things, or we can use these things in our advantage. Okay, so if you can buy a GPU for less amount of money, and we can execute a huge problem, then we are saving a lot of money. So some things like that we can achieve by saving cost and money. All right. Next thing that we will be looking at is the solve large or complete problems. Okay, so you can see that many problems are large and complex, impractical or impossible to solve in a single computer, especially given limitation computer resources. So some problems are there. We need to solve them, but we can't achieve to solve them in a single computer. Okay, so we have such examples like the grand challenge problems. These are the problems you will find list out. Let me just visit this page and show you guys. Okay, so there are like problems. You can see that they have listed out in here. They are the problems that still we are struggling to get answers. Okay, so there are problems that we need more answers, but there is no answers for these things, which the reason is behind either we do not have enough computing capacity, or we do not have the technology to solve these things. Okay, so these changes, these challenges, even they have huge impact on society. For example, the Cancer Grant Challenge, a global funding initiative to set ambitious challenge to provide diverse global team with uh, 20 million euros to come together, different things, progress against cancers in the world urgently needed. Okay, so we have a challenge to fight for cancer diseases. Okay, and these challenges still remain. We cannot get a solution. We can't get uh, we can't get something something that is promising to help with cancer treatment. Okay, so what happens in these grand challenges these are very complex in hand to and it is taking a lot of research, a lot of computational power to get it done. Even though we have some solution, okay, yeah, I think let's say for example you guys come up with something for the cancer grand challenge, and when you try to execute it, and the execution time, it shows like 100 years. Okay, we can't wait 100 years to get this done. And at the let's say we somehow we managed to get it to 100 years. At the end, we are showing okay, there was a small issue, and the problem is not solving the cancer. The problem, it has an issue, so you can't get it done. So you can't wait. You can't waste time. We can't waste time 100 years and figure out there was something wrong with the algorithm, or there is something not working that is not possible, or something like that. So these grand challenges are still in there, and you need a lot of resources to get this thing done. Okay, these things are not easy to get done. What will happen is you cannot rely on a normal computer. You can't rely on a normal computer to solve these things. Okay, you need special computers. In this scenario, parallel computers come into play, where you can execute these things and get things done. Okay, so remember these kind of examples, these kind of computers take a lot of resources, petaflops, petabyte computing resources in order to work. Okay, and the higher the complexity, the higher the computation power goes, and higher the time it takes, and we can reduce that time by using parallel computers. Okay, and there are like real world example like web search engines, database processing, and those kind of things are like not day-to-day activities that a serial computer can work with. Okay, um, so when we are talking about problems in real world, it's gonna be most of the time gonna be tight, like 99% of the time, it's gonna be something that should be handled by a parallel computer. Okay. All right. So the next thing is provide concurrency. Concurrency is doing same thing, doing something with each other uh, in a manner where two or more are doing the same thing, concurrency. So when single computer, what we can achieve is limited. That is true. That means there are some problems in the world. A single computer cannot achieve. A single computer cannot achieve this in lifetime. But a network of computers can achieve more. Okay, for example, if you look into this article by NVIDIA, so this is folding at home, crowdsourced GPU accelerated for supercomputers for COVID-19 research. Okay, so what happens is COVID-19 related researches were going on in the world. Okay, so to use these models that they come up with to fight against the coronavirus, the virus, the antidote, and everything, we need simulators for simulating protein. Okay, so I'm not a biology expert, but what I know that to fight a virus, we need some sort of protein. Okay, so the protein should be designed in a way where you can fight COVID-19 or whatever the virus that we have. So we can simulate these proteins using parallel computers. Simulating a protein structure is very dynamic, and it takes a lot of computational power in order to simulate a protein dynamics. I do not know the biology behind it. Only thing is simulating a protein and would take a huge amount of computational power. That is the given the complexity of the virus and how many inputs are there, how many parameters it will change when we are change a certain protein. Okay, the proteins, as I know, they contain a lot of inputs and outputs. So at the bottom line, we need more computational power for simulating a protein, okay, for a virus or given disease. So simulating such a protein takes high amount of computational power. That is true, but a single computer can't achieve this. You can't achieve these kind of things in one single computer that you have. You can't achieve this kind of thing where you have a lot of computers like one or two. You cannot achieve this kind of thing. It takes Um, so for comparison, a Summit World Fast supercomputer, which power more than 20,000 NVIDIA GPUs, can officially stand around 150 petaflops. That is like the um, number of computational power that has in a supercomputer in the world. But for gaining that kind of computational power, it requires 27,000 NVIDIA GPUs. So GPUs are mainly used in parallel computing. We'll see those things like the number of GPUs it needs is way too much. Okay. But even if you use that supercomputer, you will take a lot of time, a lot of energy to get this protein simulation done. So in a case where a single supercomputer can't achieve this, we can have something like we can have something like a GPU donated for other users. Like more, if you guys know, GPU play a vital role in gaming industry. Okay, if you are playing games, if you need to play new video games, what will you need first is a GPU. Okay, a GPU is a core component of gaming industry. You can't play like real fancy games with a CPU. To give that nice UI 50 frames or 60 frames per second, that kind of nice UI cannot be generated within a CPU. You need a GPU to get your gaming mode on and running. Okay, so the GPU is actually one core component to doing simulation, to do parallel computing. So what people have done is, rather than depending on one single supercomputer or depending on few of the machines available, but gamers around the world, nearly 40,000 gamers around the world, donated their GPU for this protein, simulating the protein for COVID-19. So people can share their GPU, their computational power for others to make a change in the world. A single computer could not achieve this, but what people around the world, what they gather around, they have a parallel execution hardware in their dispose. What they did was they donated that power. They will have a small program to run in the machine. What that machine will do is gonna take all the processing power available for them and donate that to get to create something useful in the world. Okay, so that kind of achievements can be only done by providing these kind of things can be only achieved by using parallel computing technologies. Okay, so you have it is something similar. The example, the COVID-19 protein situation that I explained, it is something similar to this architecture. So all over the people in the network, in this case internet, will donate their computational power in a node. That means their local machine. Sorry. So think about 40,000 of these nodes are available for finding a cure for COVID-19. Okay, that kind of concurrency can be happen if you have only provided something like this. Okay, so concurrency can be achieved. Okay, you can't achieve this in a single machine. And yes, the second thing is use non-local resources. Using compute resources in a wide area network or even internet, local computer resources are scarce and insufficient. Uh, yeah, so it's the same thing that we have talked about in the something similar to what we have talked about earlier on. Non-local resources. Okay, so non-local resources in the sense uh, what we have in our local machines or in our local computer is limited. Okay, we can't run a data center in our home. We can't actually run 1,000 GPUs unless what we are doing is profitable. We cannot use resources. We cannot execute the infrastructure. We can't handle the infrastructure that we use to execute something. So we can, but actually use non-local resources. Something, say for example, I want to utilize some GPU power, which I do not have in my local machine, but I can utilize that same computational power in someone else's computer. For example, we have computational providers like GCP, AWS. So those guys give non-local resources. If I want a GPU with NVIDIA's latest card, I can rent it out for like a couple of minutes. Okay, and I can run a model on that. Likewise, we can utilize resources which are not available in our local machine, but it is available somewhere else. Only achievable these kind of things by using parallel computing and with this architecture. You might say, okay, can't we use that the same thing with the serialization? Yes, we can, but the power of parallelization, doing it in parallel with several other computers, is not something that we can achieve in a single computer. For example, a serial computer will be, you can rent out a CPU machine with one of the cloud providers, but you can't parallelize it. You can't get it up to speed using two computers. That is not possible. But if you have parallel computing, and you can use the non-local resources where you have two machines in one of the cloud providers, and you can link them up together and to work together. If you have the right amount of money, you can actually build your own supercomputer there for like 10 minutes. You have a huge problem to get it done. And if you have the right amount of money, for 10 minutes, you can take the latest GPUs and take 100 machines and do your work, and you're done with it. Okay, so you can use non-local resources in your in your research, in your uh, in your parallel algorithm. So that's kind of power is there in the world right now. Okay, and use parallel hardware. Okay, so usage of the hardware is something much more important. So in your local machine, in your phone, you have this device which is capable of running parallel algorithms. For example, you have a GPU. You might not know that you have it, but if there is in your laptop, if you have a sticker saying NVIDIA GTX, NVIDIA RTX, that means you are having a computer that is capable of running parallel algorithms. At least you might use it for gaming or some other accelerated graphics. But remember, you have the capability of turning a problem into more executable. You can execute those things in a more powerful way by using parallelism. So even laptops, even modern computers, they are architect in a way where you have multiple processors, multiple GPUs, multiple cores. So utilization of those things. Okay, you need to uh, use that in your machines. You need to you can have more computational things get done for cheaper price. Okay, so it might take a little bit more extra resources like the like what you call the electricity and all, but if you can justify the cost by using the hardware, then you are in a win-win situation. Okay, and not only from the hardware level, but there is the software level. You can use the parallelization. We'll be using something like threads. If you're using things like coroutines, you will use coroutines as well. So in a sense where we have hardware level support as well as the software level support, we are not using those things in this way. So we should be using those things, and we can get more output than what we are using in a serial computer. Okay. So in a nutshell, what we are doing is, in most cases, serial programs running on modern computer is a potential waste of computing power. Okay, so if you have all these capabilities, you have the capabilities of running things in a uh, in a parallel computer. But if you are using serialized way of doing these things, you're potentially wasting your computing power. It's like you have a car where you can go for the speed that can achieve. It is like, let's say, 200 kilometers per hour. You can achieve that speed. Okay, but you are going at 50 kilometers per hour. Okay, you are under using your resources. If you utilize it correctly, you can go much faster. Okay, known fact, if I'm not mistaken, the fuel consumption of a car is at its highest. The consumption and the utilization is highest at least it's in its top speed. Okay, so you need to use your computing power without wasting your potential computing resources. Like electricity, that we are using for produce something is should be something useful rather than where we are using for some non-parallel task. Okay, you have great computer which can do great things, but you are underusing it. So use the parallel hardware that we can take, then take the advantage of it. All right, so we talked about what are the advantages of using that, what sort of things that we can achieve, and what sort of things we should do, and what sort of impact that we have in using the parallel computing, and why it is so important, why it is so useful in real world. Okay, I'm not saying that parallel computing, that you should always do parallel computing, no serial computing from anywhere. No, that is not the case. In certain situation, in most of the time, the real world situations, parallel computing is at its peak. Okay, but for other things, for other um, other smaller things, we can use serialization to achieve the same thing. Okay, all right. So any questions up until this point? So we talked about serialization, we talked about parallelization, what are the enabling factors for parallelization, and why potentially we use parallel computing. Okay, Hope everything is clear. These things are like mostly in what do you call theory. So these theories you can get without an issue. All right. Next, we will talk about concepts and terminologies that we need to know when we are dealing with the modern day computers. Probably you guys have heard about these architectural patterns, but we'll go on a refresher because the architectural pattern that we are using today is something fundamental for parallel computing and how these instructions are executed that we should know. So these are like the basic computer architecture that we use. Von Neumann architecture. This is the architecture currently any accessible machine we are using, unless you are using a quantum computer. Okay, for general users, whatever the machine we are using, whether it is Intel, AMD, Macintosh, or anything like ARM, we'll be using this von Neumann architecture for modeling our computers and its resources. Okay, so the von Neumann architecture is named after a mathematician, John von Neumann, who authorized the general requirement for electronics in 1954. So, honor of him, we are naming this. We also call this stored program computer. The program is stored somewhere else and executed in somewhere else. Both program and instruction data in electronic memory. Okay, so the program that we want to execute and the instructions that we are going to execute are both in electronic memory. For example, in this architecture, we have something called the memory. Okay, you guys can see it in and down there. We have several memory types, long storage and short storage. So most of the time, the program what we have to get executed, if it is not loaded to memory, we load it from long storage for short storage. Then we execute that program in short storage. Once the execution is done, we will sometimes save some data for the long storage, or we might not. So classical example is like when we want to run a program, what we do is first we need to make sure the program is installed in our hard disk, the long storage in this scenario. So when we want to execute some program, let's say for example a game that we have installed, okay, the game, not all the component from the game, from the long storage, which means the hard disk or SSD, whatever the long storage device we have, we copy that instruction, the program, into our memory, which is short storage, which will be like our RAM. Okay, so once the program is copied to our memory, the CPU is getting those instructions, the problem that we are trying to save from the memory, and we execute those things and we get the result. Okay, so we have these memories. We have those everything electronic memories, which is, do not think about like how it was there, but right now remember the instructions are kept in a way where we have both the program and the instruction are in a memory. Okay, so virtually all programs follow the basic design. Okay, any computer right now, even your phones, unless, as I mentioned, if you're using a quantum computer, you will be using this basic architecture. Okay, so in a classical computer, in a classical computing architecture, you will find these four main components: the memory, control unit, arithmetic and logic unit, and inputs and outputs. So these are like the foremost base components if you find in your computer. This is the things that you will see. So most of the time you guys know that control unit and arithmetic and logic unit compose the CPU, which we call most of the time central processing unit. And the central processing unit is getting inputs and outputs, and the memory is somewhere we get all the data from. Okay. And we have read-write random access memory used to store program and instructions and data. So memory in this scenario, what we call random access memory, or we call RAM for short. So everything that we want to execute, the program itself and the instructions, those all are in this memory. Okay, so memory is the place where we store our instruction, and instruction get executed in the CPU itself. Okay, it's gonna execute these things in our CPU. The memory is just where you store the program, the instructions and all those things. Where they get executed is within the CPU. Okay. So we have programs and instruction are coded and data shell computers to do something. Okay, the instructions say add, the arithmetic logic unit add. If it is a divide, it's a divide. So all those things comes in the instruction set. As you guys know that computers are not capable of doing certain arithmetic operations, but they do in a workaround. Have a look around it. It's an interesting fact. There are certain arithmetic operation a simple computer can't do. Okay, that is something interesting. Have a look around it. But anyhow, they have a set of instructions within memory. These instructions get executed over the CPU. Okay, data is simply information used by the programs. Of course, we need to provide inputs and outputs for the instructions. We will see in a little bit how we do these things as in a computer. Okay. So control units is fetching instruction from the memory, decode the instruction, and sequential coordinate operation to accomplish the program task. So this is one of the important things. And control unit is fetching the instruction from the memory. So whenever we want to fetch something, what is the next instruction that we need to execute? What is the next instruction we need to work on? The control unit is the section where it is in that section. So as name suggests, it's control the instructions. Okay, whether we want to copy something, whether we want to copy back something from the CPU to memory, the control unit is the person who is taking in and out instruction from the memory itself. Okay. So the next thing is arithmetic is the base operating section. That means control unit take an instruction, but they do not execute anything. They manage the instructions, they manage the read write, but not the execution. Execution happen in arithmetic and logic unit, ALU. So the flow is normally instruction will be from longer storage. It will copy to memory, which is RAM. Then the control unit will have communication with memory saying what are the instructions that I need to execute, give me those instructions. And once the memory supply those instructions, the control unit will give those instructions to ALU, arithmetic logic. Okay, I got some instruction, execute these things, give me back the results. Once the results is back, they might be stored back in the memory, or they will just perform an action. Okay, so this is how a modern or at least right now what we are using, a computer works. So to work with this instruction, we might need some inputs and outputs. Those inputs and outputs are provided by human interface or human operator, where we can input things like from a keyboard or a mouse, or we can instruct the machine to get some data from the internet. Whatever we do is we have some inputs and we get the output based on the instruction that we provide. Okay, so remember this basic architecture, because it's gonna introduce a lot of things related to CPU programming and CPU and GPU programming. But basic architecture for any computer that we have is 4 of these basic control units, and they execute instruction. That's it. So we in instruction execution, so this is like the anatomy of the computer, and the Finn's classical taxonomy, which is gonna be like a classification of how we do this instruction execution. Okay, so this is like the way we do it, and these are the different way of doing it. Okay, so we do not want to get these two things mixed up. So this is how it is doing it. Okay, any model, anyhow, at the end the instruction get executed this way, and these are the different way of executing these instructions. Okay, there can be different way of instruction execution depending on the way the instruction execute. We call either it is a serial execution or a parallel execution. Okay, so let's see what is this taxonomy, Finn's classical taxonomy is explaining to us, and see the boundaries of instruction execution and what we can get out of these things. One of the most widely used classification since 1966, okay, Finn's taxonomy describes a multiple process computer architecture according to how they can be classified along with 2 independent dimensions of instruction stream and data stream. Each of these dimensions can have only 1 or 2 possible strategies, single or multiple. Okay, so we have 2 things to consider at this point. So we have instructions. We have instructions which is stored in our memory, and we have data. Okay, we have data which we use for instruction execution. Okay, instructions is like the operator that we are going to do, and the data is what these operators are based upon. Okay, so let's take a classical example, and we have 2 plus 2. Okay, so 2 plus 2 is kind of the problem. Okay, so the data in this scenario is let's say 2 plus 3, otherwise it will get confused. 2 plus 3 is our instruction, is our problem, and the data for this instruction is 2 and 3. Okay, 2 and 3 is the data for our instruction, and the operator that we're going to be executing, the instruction that we're going to be executing is sum or plus. Okay, so depending on the classification, okay, we can have single or multiple instructions or data. Okay, we can have a single instruction or we can have a multiple instruction. We can have single data or we can have multiple data. Okay, based on these 4 categories, based on these 4 different types, we come up with 4 different classifications. Okay, so this classification is based on the type of instructions and type of data that we have. So we have two types from each, where we can have single instruction or we can have multiple instructions, or we can have single data or multiple data. So those are the four combinations that we have. Four combinations we have: single, multiple, data, or instruction. Okay. So based on these combinations, we have possible classifications. So we will look into each and every one and see how these things are falling under the category of uh, falling under the four categories, and whether they are serial or they are uh, parallel. Okay, so let's take the four type and try to come up with the four classification. So we have single instruction stream and single data stream. So that is the basic component. So we have a single instruction and we have the single data stream. Okay, one instruction and one data stream. And the second type is we have the single instruction stream. Okay, we have only one instruction in our stream, but we have multiple data to work with. Okay, so we have single instruction, but now the data is multiple data stream. And the third one is multiple instruction. Okay, there is not only one instruction, but multiple instruction coming in, but the data stream is single. Okay. And for last, we have multiple instruction. We have multiple instructions coming in. The instructions they have different types. And the data that we are getting is also multiple data stream. Okay, so let's go one by one and let's get more clarification on each. Right now, remember the four variant: single instruction, single data; single instruction, multiple data; multiple instruction, single data; multiple instruction, multiple data. So these are the four variants that we can come up with depending on the singularity or multiplicity based on instruction and data. Okay, so let's see the first type. So you will guys get a better idea what we are talking in here. So we have single instruction and single data. Single instruction, single data. We call this a basic serial or non-parallel computing structure. So as name suggests, it's have a single instruction and single data. Okay. A single instruction, what do you mean by single instruction? One instruction in the stream being acted by the GPU during any clock cycle. That means when we are executing some instruction, okay, when we are executing, if you guys can remember, at a given moment, we call the clock cycle, one instruction stream is being used. You don't have multiple instructions coming in. You have only one instruction that is in the that is within the clock cycle. So you do not have any other instructions coming in, only one. The single data means only one data stream be used for the input for the one clock cycle. That means when we are executing the instruction from the instruction pool and from the data, we get only one data stream. We do not have multiple data. So we have only one data pool, one instruction pool. So it's automatically coming in the serial computation. Let's see more in order. So deterministic execution, yes, the deterministic execution is there because we have one instruction and one data. We execute that, we get the result. This is the oldest type of computers. That means these are like these are since the birth of computers. So we have one single instruction, single data type. That's it. Older generation mainframes, mini computers, workstations, single processor computers, CPUs, anywhere, any older generations of computers. This is the architecture that that is being using. Okay, even some computers up until today is using that. And if you guys can remember the chip that I showed you earlier, this one, we call this ESP32. ESP32. This one is something similar to SISD. Single instruction, single data source. Okay, so let's see in illustration. So this is the one that you guys need to memorize. So at a given time, this is one of the clock cycle that we have visualized. So at a given time, we have single instruction. So throughout the time, you guys can see one instruction is there. Load A. Load A is one instruction. Load B is another instruction. And C is equal to A plus B and store C. And the third instruction is A equal to B multiplied by 2 and store A. So you guys can see only one instruction at a given time is executed. Okay, and one single data source is used in this scenario. Okay, so let's take a mental picture of this. We have a processing unit, one instruction pool, and one data pool. Then we go to the second one, the single instruction, multiple data. Okay, so we have single instruction, a type of parallel computing. Okay, this is all the processing unit execute the same instruction at a given clock cycle. That means we have multiple processing units. You can see PU, multiple PUs are there. But the thing is, the instruction pool has single instruction. That means whatever the given time, each and every this processing unit will have the same instruction. The instruction will not change at a given time. Okay, but the data that is of each of these processing units will take in will differ. Okay, will differ at a given time. So single instruction is executed on each and every one, and multiple data is fed onto these processing units. Best suit for specialized probleming characterize a high degree of regularity, such as graphic and image processing. So if you are working with something like graphics processing, image processing, so this is the architecture that we are using. Okay, so when we are talking about GPUs, when we are talking about image processing and everything that in between, this is the architecture that we are using. In a GPU, when we talked about, we will talk about GPU architecture in much more detail. But in a nutshell, GPU architecture use the single instruction multiple data. So in a GPU core, you will find one single instruction, but depending on the data source, it will have different data. Okay, instruction is same, but the data is different. So this is high regularity. Since the instruction is same, it's going to be the regular instruction for each and every one. Synchronous key blocks in the deterministic execution. That means each and every instruction is going to executed in this processing unit is same. So we can have deterministic output because it's only varying on the data that we are providing. Okay. So these are like the processor variants. These are not like that much, not super important. Modern computers, particularly those graphic processing GPUs, employ the SIMD instruction and execution unit. So basic thing to remember, if you're using a GPU, this is the architecture that is going to use. Okay, so let's take it in a visualized manner. So you guys can see there are throughout the time there will be multiple processing units. In here we have shown 4 processing units, but in here we are showing only 3. But that doesn't matter. Even you have like 1,000 processing units, this is going to be the same. So we have like P1, P2, and Pn. That means any number of processing units that you have. Okay. The instruction, look at the instruction. Preview, instruct, preview, instruct, preview, instruct. So the instruction is for at a given time, at a clock cycle, all the instructions are same. Okay. And you guys can see the data, the instruction for the second cycle is also the same. Load A, load A, load A. Okay, the instruction is same, but you guys can see the data that we are using, it's going to be different. So for instruction is load A, but the data pool is 1. Load A, you will be loading A, but it is coming from pool, data pool 1. You will use the second processing unit. It's going to also load A, but the data source is not 1, but it is 2. As so the list goes on. N amount of data sources, if there are, n amount of data sources, if there are, they will use that. Okay, so instruction is same, that is a single instruction as the name hints. The multiple data, the data source is for first processing unit is 1, for the second one it is 2, for the nth unit it is going to be n. Okay, so if you look at this next instruction, as I mentioned, the next clock cycle, they will all have the same instruction, load B, load B, load B. But the data pool, the data that we are taking is for P1, it is going to be 1 data source. For P2, the processing 2, it will be the second data source, and list goes for N. The N data source is used. So if you look at the next step, you guys can see the instruction is same, data source is different. Instruction is same, data source is different, and instruction is same, data source is different. Okay, so in this processing architecture, SIMD, the instruction is going to be same, but the data source that we are referring is going to be different. So that's the hence name, single instruction, multiple data comes in. Okay. If you look at once back, again in the single instruction, single data, the instruction is same. Okay, we do not have multiple processing unit. So load A, load B, the data pool is also 1, and all the instruction, the life cycle happens only at one time. You don't have multiple processing unit, so you don't get parallelism in this architecture, but you get the serialization and you get the picture. They have one single instruction, one single data source. That's it. But in here, you have multiple data sources, but one single instruction. All at a given time, at a given clock cycle, all the processing unit execute the same instruction, but the data source that they are using is going to be different based on the data pool that they are connected with. Okay, all make sense, everybody? If you get the idea, please raise your hand. You can use the Zoom raise hand function. Hello. Raise your hand if you get the difference between single instruction, multiple data, SMMD and SISD. Okay. Okay, 3 people. Hope everyone gets it. What about others? Others did not get the things. Samadhi, Harshana, Ishan. Did you get the idea behind single instruction, single data, multiple instruction, multiple data. What about others? Only 5. There are like 10 here. Prashant, did you get the difference between those two? What about Ajit? Vitoshana?
Yes, sir, I got it, but I couldn't find the hand sign.
Okay. It's somewhere on the more section, and I'm not sure. I haven't raised my hand. Well, I'm not sure. I have no idea, actually. Okay, as long as you get the idea, it's fine. So you get the single instruction, single data, multiple instruction, sorry, single instruction, multiple data. So these are like the two things that we have talked so far: serial computing and parallel computing. So this thing is still in use. This thing is heavily used even today with GPUs and everything. And we will go more into multiple instructions, single data. Okay, as you guys can get a type of parallel computing, because we have multiple instruction coming in. Okay, there will be multiple instruction, but all these instructions will be executing the same data. Okay, you guys can see the instruction for this processing unit is going to be same. Sorry, multiple instruction. So the first processing unit will get a different instruction. The second one is also going to get a different instruction. But the data that we are retrieving is going to be same. Okay. Multiple instruction, each processing unit operate independently. We are separate instruction scene. Single data, that means every single processing unit will get a single unit. Few, if any, actual example of these parallel computers have ever existed. That means this is like not a use case that you will see each and every day. Okay, these kind of instruction are very rare, or even you can't find examples on this. It's like an extinct model, but still the concept is there. I mean, how it should operate theoretically, but in practical, you won't find anything that is in use for MISD. Okay, let's look at the mental picture, or the picture that you will see in here. So as I mentioned earlier, the instruction pool will give instruction. So you can see that instruction in here. It is the same preview instruct, the load A. Okay, these are executing load A. That doesn't mean like the instruction pool is like giving all the instruction randomly. They can have the same one, but if you look at the instruction pool in here, first processing unit, the P1 is executing C1 equal A1 multiplied by A, and the second one is using delta A1 multiplied by 4. The nth one, they can have mat n, and data stream is A1. Okay, so you guys can see that the operation, the instruction they are using is different on each processing unit, but the data unit, the data pool is same: A1, A1, and A1. Okay, so no matter what the instruction is, the data pool is same, but the instruction is different. So the next instruction you can see, for P1 it is store, for P2 it is BI, PSI plus 8, P for PN, it is going to be different. Okay, so the instruction keep changing, but the data input stream, it is going to be same. Okay, so you guys can see the complexity of handling such a thing. So you have multiple instruction, multiple So multiple instruction is there and data is different, and each and everything are basically doing their own type of thing, but the data is keep changing. Okay, so these kind of things are really extinct, or they are not in use for practical usage. Okay. All right, the last one, multiple instructions and multiple data, MIMD. Okay, a type of parallel computing, as you can see. So each and every instruction, each and every processing unit get a different instruction pool, and they get a different data pool, multiple data pool. There can be there will be multiple data pools for each and every processing unit. Okay, so if you look at the data pool, there can be multiple ones. So multiple instruction, every processor may be executing different instruction stream. So if this one is doing one instruction, this one will be doing another. That varies. And this processing unit will have one data stream, but this processing unit might have another data stream. We can't guarantee that the first one and the second one is using the same data stream. We can't guarantee that. Execution can be synchronous or asynchronous, deterministic or non-deterministic. That means execution of these things can be done in a way that each and every one is not depending on another. That means synchronous, one after another will get executed. Or it can be asynchronous. That means we are not waiting one after another. If PU, in this scenario, this processing unit is executing something, and it might not depending on the second processing unit. This second processing unit is not depending on they are executing this data individually. The reason behind is that instructions are changed, the data is changed, so they do not they might not have a connection between these things. But sometimes they might have a connection between these things. That is called the synchronous process. The instruction that provide in here, PU, might get affected to the second one, because that the execution of this will be the input for the second PU processing unit. So that will be synchronous. Okay, that in a sense, where we have this processing unit depending on each other, that is synchronous. And there can be places where these processing units are independent from each other, that is asynchronous. Okay, that can be any of these things happening at a given life cycle. We can't say, okay, this is going to be asynchronous, this can be asynchronous. Depending on the instruction that we are trying to execute, it may differ. And the output can be deterministic or non-deterministic based on the instruction type that we are executing, whether it's synchronous or asynchronous. We can predict, okay, PU1 will give this instruction, but the same PU that we will have in here will give the same instruction. That is not going to work, because the instruction is changed, the data pool is changed, the way data getting into this pool is changed. So we can't exactly say deterministic output is there, or it can be non-deterministic. The same goes for the other way around. If we are using the same pool for two different processing unit and the same data, then it is deterministic. But if you are using two different data pools, two different instructions, it is non-deterministic. We can't guarantee every processing unit to have the same output. Unless they get the same instruction and same data pool, they will be different. So it can be deterministic, non-deterministic. Currently, the most common type of parallel computer, most modern supercomputers fall into this category. Example, most current supercomputers, network parallel computers, clusters, grid, multiprocess, SMPs, computers, multi-core PCs. So the computers that you might having right now, where you have multiple cores, where you have multiple processors, probably you will have multiple cores, comes under this instruction category. So this is like the computer that you will be using, the phone that you are using, might come under this MIMD architecture. So this is probably the place your computer, your phone, your computer, your phone is coming. Okay, so make sure you have this architecture memorized. Let's see in a diagram. So you can see that at a given clock cycle, the preview instruction is executed, and you can see the P1 is doing load A1. It is using the instruction load A and the data stream 1. But for the P2, they are doing completely different instruction called function D, and they are not using even the same instruction, same data source. Okay, data pool is different. So the third one, OPN1, is doing do 10 iteration for n, and you guys can see the data source. It can be different. We can't guarantee that we have the same data source as the same life cycle. So in here, the second instruction is load B1, and the P2 is doing completely different multiplication, and the PN1, it is also doing the same. Same goes for the other processes as well. So you guys can see that each and every processing unit is executing its own instruction and on their own data pool. Okay, so this is kind of like the structure that you will see in most of the common computers that we use. So we have 4 anatomies. Out of them, MIMD is what we are using right now most of the time. Our phones, our tablets, our CPUs, it's going to be multiple instruction, multiple data. And we have multiple instruction single data, which is like an extinct version. We do not have these things in real life use case. Those are like did not actually exist even. These are not viable use case for computing. And we have SIMD, which also we use into day-to-day activities, like when you're doing GPU processing. Even in your phones, you might have GPU enabled, so single instructions in multiple data. And for older computers, as I mentioned, where like very low power applications are there, you might see these single instruction, single data sources. Okay, so out of four multiple instruction, single data is no longer in use. Single instruction, single data is barely used, where you will find in all computers. But SMIND, that means single instruction, multiple data, and multiple instruction, multiple data is one of the heavily used ones as of today. Okay, so you guys can see that these things are connected to each other. These things are working with some working with these anatomies, and these things are used in real world, and you guys need to know what is the difference between these things, and what are the use cases, and which are extinct, which are not in use, which are commonly used, and what are the instruction, what are the applications that these things are used in. Okay, so we talked about the von Neumann architecture as well as Finn's classical taxonomy. Okay, so these 4 things you guys should have in memory, so you know how our computers work, how what is the general architecture and what is more sophisticated architecture based on the instructions and the data that we provide. Okay, any questions up until this? Hope not. All right. So the next one is instruction that shows for with SMID, that single instruction multiple data, which is a representation of like GPU processing. We will have a separate discussion on this. Right now, you guys can see physical hardware, how we are going to do these things. So the instruction is for a given clock cycle. In this scenario, the first one is the add, the single instruction. Current instruction is add, and you have several processing unit, and you have multiple data sources, R1, R2, R2, R1, R2, R1, R2, R1. So multiple data sources are coming. At least in here, we have 2 data sources. Okay. And the currently it's going to produce a single output, which is called R3. Okay. So one thing that you guys need to remember in this SMID architecture. So you will hear this statement a lot, like you have a GPU, and the GPU will have 5,000 cores. Okay, so that's not true. Okay, the GPU cannot have 5,000 cores or something like that. Cores is a different concept. If you guys can remember, a core should consist 2 things. Okay, if you are talking about a core, you need to have the control unit as well as the arithmetic logic ALUs. But simply saying 5,000 cores is there in a GPU, that simply they are referring there will be 5,000 ALUs, arithmetic logic units. As you can see, the instruction is the same, that what we are meaning in here, you guys can see that in this architecture, the instructions are fetched by the control unit. Okay, the control unit is fetching instruction, and in this scenario, the control unit is fetching one single instruction. Okay, the control unit is one single instruction, but the arithmetic and logic unit will have different things to execute. The data that they are going to be executing is different. So if somebody says a GPU, okay, your GPU contains 5,000 cores, they're wrong. What they are actually meaning is they have 5,000 arithmetic logics units, ALUs, within their dispose. They have one single control unit which feed the one single instruction. Okay, so you might think, okay, if a GPU can have 5,000 cores, if GPUs can have 5,000 cores or 5,000 arithmetic units, why don't we build our machines using GPUs? Okay, why do we need CPUs? CPU is having less cores and less amount of things to do. Okay, there will be more execution time in GPUs. GPU have so many cores, so many arithmetic logic units. Rather than using the CPU, why don't we use GPUs? So the main reason, if you look at the mental model of MIMD and SMID, the computer, the CPU, the normal day-to-day computer or phone, they perform multiple tasks. They do not perform one singular task at a given moment, and they have different data sources. For example, let's take this my computer at right now. Okay, so there are several tasks, at least what I'm visualizing in here. There can be several tasks going on at the given moment. So my cursor is moving, that is one task. It has one input and one output, one input from my mouse, and another task is running my browser. Okay, that is running several things at hand, and it is rendering graphics in here. When I am hovering over, the graphics change, so the graphic is changing. as at the same time my mouse moves, at the same time my internet works, my network traffic is coming on, at the same time my battery is monitored, same time my Zoom meeting is getting recorded. So multiple instructions happens, okay, not the same thing, multiple instruction happen in my machine. Okay, so if you guys can remember, in a GPU, you cannot have multiple instruction executed. So if you have all, if you remove your CPU and put up GPU in your machine, what will happen is you can do you can do one of those things at a given time, as example. Okay, so if you move your mouse, then GPU will be only able to process the mouse movement because it is single instructed. You can have multiple data, but it's going to be doing one instruction set at a given time. But your CPU, central processing unit, it can handle multiple data, multiple instructions, so they can do multiple tasks at once. Okay, so that's why the main reason you don't have GPUs in your machine, but rather than you have CPU and GPU separately within your machine. So CPU can handle variable instructions, which are like handling these complex tasks. If something like graphical processing unit task is coming in, CPU fails. CPU is good at doing multiple tasks, but not one single task for different data. So GPU come in handy if you are doing some graphical unit graphical tasks. So like rendering a game, they have the same instruction, but